Welcome back to Smash Study Trigonometry. Last time we discussed what an angle was and how to measure angles. In this episode, we're going to have 3 times the fun because we aren't going to just be talking about one angle, we're going to be talking about 3 of them. That's right, we're going to start to explore the amazing world of triangles. Triangles are an incredible shape. They form the foundation of most other shapes and is the fundamental object in trigonometry. In fact, trigonometry comes from a Greek term that literally means triangle measurement. Triangles themselves are used all over the place. We use them when we triangulate a position. Surveyors use triangles to measure the height of distant objects. There are countless triangles in construction, physics, city planning, engineering, and more. Pretty much anytime you have shapes and need to measure things, triangles show up. It even makes that cute little sound in orchestras. So what is it about triangles that make them so important? Well, one important quality is that every polygon can be cut up into triangles. That's why I said that triangles form the foundations of other shapes. Because of this especially important fact, we can obtain several facts about polygons by looking at the triangles within them. For example, we can find the area of a polygon by adding up the areas of the triangles that the polygon is cut into. Since all these polygons are conglomerations of triangles, understanding how triangles behave is key if we want to understand how general polygons, or really geometry, works in general. In fact, in more complicated situations where the space we are talking about might be curved, we can identify how that space is curved by how the triangles in that space work. And that's why today we are going to talk about all the important properties of triangles in the regular flat Euclidean geometry where trigonometry works. In fact, we'll make at least 3 points repeatedly. You get it? It's funny because of the 3 points. Just roll the credits. Welcome back to our video series on trigonometry. Today, we find ourselves seeking out triangles in the wild. Look over here and be quiet so that we don't scare it away. See these 3 mighty angles here and the 3 stalwart sides. The strength they provide in this natural setting is truly majestic. Oh, how did he get back in here? Sorry about that. Anyway, today we are talking about triangles. A triangle is a shape made out of the 3 line segments called sides between 3 points called vertices that are not on a line together. Another way to think about it is it's the shape formed by 3 mutually non-parallel lines. Each pair of sides intersect at a vertex and form an angle at every vertex. Since there are 3 vertices, we get 3 angles inside. The Greek and Latin prefix for 3 is tri, and so 3 angles becomes triangle. Yeah, mathematicians are quite creative with the names we use. In this video, we'll talk about several properties of triangles that will be important in our study of trigonometry. I'll point out here that the properties of triangles we describe are specifically the properties of triangles that exist in Euclidean plane geometry. While we won't talk about it in this series, it's interesting that some of these properties are not true if you draw triangles in other kinds of spaces. There are a few scholar-sauce videos about that, but like I said, we won't talk about that here. Now, because triangles are so important, we use special names for various types of triangles. Some of these names tell us about relationships between the angles, while others tell us about relationships between the sides. Let's talk about some of these types of triangles that emphasize specific relationships between angles. First, it's true that in every triangle, at least 2 angles in the triangle are acute, that is, less than 90 degrees in measure. What the third angle does is how we identify the following triangles. An acute triangle is a triangle where all 3 angles are acute. A right triangle is a triangle where one of the angles is a right angle. In a right triangle, the side opposite the right angle is called the hypotenuse, while the other 2 sides are called legs. An obtuse triangle is a triangle where one of the angles is an obtuse angle. You can think of these names as identifying what happens with that third angle that isn't guaranteed to be acute. Since that third angle can be exactly one of acute, right, or obtuse, this tells us that every triangle is exactly one of these 3 types that we talked about. The most important type of these triangles is the right triangle, and not just because it wins every argument it's in. Actually, right triangles will form the foundation of the trigonometric functions that we'll study as we go. There are also some very important facts that are true about right triangles that have become immensely useful later on, so we'll come back to right triangles a lot. The last type of triangle that talks about a relationship between the angles is called an equiangular triangle. This is a triangle where all three angles inside are congruent, which means that they have the same measure. Since at least two of these angles have to be acute, every equiangular triangle is also an acute triangle. The next types of triangles refer to relationships of their sides. A scalene triangle is a triangle where no two sides have the same length. An isosceles triangle is a triangle where two sides have the same length. An equilateral triangle is a triangle where all three sides have the same length. Wow, that's a lot of words to keep track of. This is one of the trickier parts of mathematics. There are two really important goals in mathematics. The first is that mathematics aims to explain why various things happen. This requires math to deal with complicated concepts in extreme detail, and there are a lot of things to keep track of. The second goal of mathematics is to communicate these complicated explanations accurately and efficiently. This requires us to build language around various concepts. Part of this requires us to have a wide and precise vocabulary, and that's what all these words are for. It does take some time to get used to them, but once you master the vocabulary words in mathematics, you have so much more power to understand the bigger ideas that math is trying to describe. Now that we know various types of triangles, we need to review several facts about them, as we will use many of these as we learn about trigonometry. The first set of facts has to do with what it means for two triangles to be congruent. I think this is the perfect place to have Number Man help us out. Take it away, my friend. Triangle congruency is an important concept in geometry. Saying two triangles are congruent means that they measure the same in every way. Specifically, it means 6 separate congruencies. If you line up the sides and angles, two triangles are congruent if each pair of corresponding sides and each pair of corresponding angles are congruent. There's 3 sides and 3 angles, so that's 6 separate congruencies. Now, what's cool is that there are some instances where it is only necessary to check 3 of these congruencies to get the other 3 for free. And these are the triangle congruency criteria theorems. The first criteria is side angle side, or SAS. What this means is that if we have 2 triangles and we find that 2 of the corresponding pairs of sides are congruent and the corresponding angles between them are also congruent, then the 2 triangles are congruent, meaning the other 2 pairs of corresponding angles and the remaining pair of corresponding sides are also congruent. Another criteria is angle side angle, or ASA. This means that if 2 triangles have 2 corresponding pairs of angles that are congruent and the corresponding sides between them are also congruent, then the 2 triangles are congruent. Then there is angle angle side, or AAS. This is similar to the last one, but in this case, if 2 triangles have 2 corresponding pairs of angles that are congruent and a pair of corresponding sides not between them that is also congruent, then the 2 triangles are congruent. Next, there's side side side, or SSS. Here, if 2 triangles are such that each pair of corresponding sides are congruent, then the triangles are congruent. That is, the corresponding angles will also be congruent. You might notice that I left out side side angle, or SSA. I guess you could spell it the other way, but we want to keep this kid appropriate. This is because SSA is not generally a congruency criteria. For example, here you have SSA, but have 2 non-congruent triangles. However, if the triangles are right triangles with the right angles being the congruent pair, then you do get congruent triangles. This is called the hypotenuse leg theorem because the 2 pairs of congruent corresponding sides will include the hypotenuse and a leg. Finally, angle angle angle, or AAA, is not a congruency condition either, but it is an important relationship. If 2 triangles have all pairs of corresponding angles congruent, then the corresponding sides might not be congruent, but they do have an interesting relationship. We call any such 2 triangles similar. This will be a key idea in trigonometry, but Alan will tell you all about them in a moment. Thanks a lot, Number Man. In addition to these triangle congruency conditions, we actually know a huge number of facts about triangles, and many of these will be very important as we study trigonometry. First, the sum of the measures of the 3 angles of any triangle, or its angle sum, is always the same, exactly 180 degrees. Give it a try. Get out a straight edge and a protractor and draw a few triangles as different as you can make them. Then measure the 3 angles of each triangle and add them together. You'll find that no matter what triangle you draw, the angles always add to 180. Go ahead and pause the video and try it out. That's pretty cool, huh? Next is the triangle inequality. This says that the length of any side of a triangle is strictly less than the sum of the lengths of the other two sides. You can see this if you straighten out the other two sides into a parallel line segment to the first one. It's always going to be longer because it has to move off the straight line path between the vertices and then come back down. So this is a version of the statement that the shortest distance between 2 points is a line. Curiously, both the fact that the angle sum of a triangle is 180 and that the shortest distance between 2 points is a line are only true if you're drawing pictures on a flat surface. If you try to draw pictures on a curved shape, then these facts are no longer necessarily true. There are a couple of scholar sauce videos, like I said, that discuss those ideas with links in the description, but traditional trigonometry is done using the geometry of a flat surface, and so we won't need to worry about these facts here. The fact that the angle sum of a triangle is 180 also provides us another fact. An exterior angle to a triangle is one that's formed by extending one of the edges past the triangle and considering the angle there that is a linear pair of the angle inside the triangle. Since those two angles are supplementary and add to 180, the measure of this exterior angle is equal to the sum of the other two angles in the triangle and hence is greater than either one individually. Another theorem relates the measure of the angles in a triangle to the lengths of the sides opposite them. In a triangle, the largest angle is always opposite the longest side, while the smallest angle is always opposite the shortest side. In fact, this tells us something about isosceles triangles. If you have two congruent angles in a triangle, then the opposite sides are congruent and vice versa. This makes that triangle isosceles. The most famous theorem about triangles is, of course, the Pythagorean theorem. This says that in right triangles, the sum of the squares of the lengths of the two legs of the triangle is equal to the square of the length of the hypotenuse. If we call the lengths of the legs A and B and the length of the hypotenuse C, this fact becomes the more familiar A squared plus B squared equals C squared. This theorem is named for the Greek mathematician Pythagoras, but it was actually known long before him. Both ancient Babylon and ancient Egypt were aware of this fact about triangles almost 1400 years before Pythagoras made the fact popular. Beyond that, the Pythagorean theorem can actually be generalized a little. If you consider a right triangle and keep the lengths of the legs fixed, you can see that if we increase the size of the right angle to make it obtuse, it'll make the length of the side C longer. Similarly, if we decrease the size of the right angle to make it acute, it makes the length of the side C shorter. Since the lengths of A and B stay the same, this leads us to the following Pythagorean inequalities. If the triangle is obtuse and C is the side opposite the obtuse angle, then A squared plus B squared is less than C squared. While if the triangle is acute, then A squared plus B squared is greater than C squared. We'll see another way to arrive at this fact when we learn the law of cosines a little later in the course. Finally, we come to one of the most important theorems in triangle geometry, and it's the first foundational property that makes trigonometry work, though it doesn't seem to get as much hype as the Pythagorean theorem. And that's the notion of similar triangles. As Numberman mentioned, this happens when the corresponding angles in two triangles are congruent. This isn't a congruency condition because we can still scale the triangles up and maintain the angle measures as long as we scale the triangle the same way on every side. And this is actually what the fundamental theorem of similar triangles says. That is, if we come across two triangles that have the exact same angle measures, then the two triangles must be scaled up or down versions of each other. Put another way, given two similar triangles, the ratio of two corresponding sides of each triangle will always be the same, no matter which corresponding pair one uses. This is another example you can try at home. Use your protractor and straight edge to make two different sized triangles with exactly the same angles. You'll find that if you then measure the corresponding side lengths and take their respective ratios, you'll always get the same number. This scale factor is how much bigger or smaller one triangle is than the other. Go ahead and pause the video to give it a try. This allows us to make one final observation. If we have two similar triangles and they have corresponding sides with A and K and B with M, then we have from the fact that triangles are similar that A divided by K equals B divided by M. But multiplying both sides of this equation by K over B yields that A divided by B equals K divided by M. So the ratio of the two sides of the first triangle, AB, is equal to the ratio of the same two corresponding sides in the second triangle. That is, the ratios of any two sides of a triangle don't change when we scale the triangle up or down as long as we keep the angles the same. This will be critical when we talk about right triangle trigonometry next time. I hope you'll join me, and yeah, I know I didn't tell as many jokes this time around, but come on, triangles are clearly no laughing matter. Anyway, if you haven't already, please like this video and subscribe to Scholar Sauce. It really helps us create new content for you similar to this. Anyway, we'll see you next time on Smash Study Trigonometry.